This is the Chapter 2 vocab video for Chem 100. The first term is alpha particle, and alpha is a Greek letter. It looks kind of like a little fish. And an alpha particle is a type of radioactive particle. It is made of 2 protons and 2 neutrons, so it has a mass of 4 AMUs, and the symbol for it is the same symbol for a helium atom. It's basically a positively charged helium nucleus that can get shot out of large atoms as they rearrange their subatomic particles. So that's an alpha particle. It's the largest type of radioactive particle, and so it's actually most easily stopped, so it's not very penetrative. Atomic mass is the mass of an atom. Did I get that right? No, I'm thinking of the mass number. Atomic mass is the average mass of all the atoms of an element. So it's the number that's reported on the periodic table on the bottom of the square. So like 26.899. I just made that up. I don't know if that's an actual atomic mass, but it's actually an average mass of all of the isotopes of isotopes of an element. So atomic mass is found on the periodic table. It's the bottom number in each square. Atomic mass unit, AMU, is the mass unit for atoms. Since they're so teeny, 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 tiny, like we can't even use milligrams or micrograms or picograms are not even small enough of a unit. So we had to create a unit to measure them. So we call them atomic mass units. They're just itty bitty mass units. The atomic number is also found on the periodic table. It is the number on top of the symbol, and it also happens to represent the number of protons that are present in all atoms of that element. So helium, it has an atomic number of 2 up here on top of its He symbol, and that means that every helium atom has 2 protons in it. A beta particle is another type of radioactive particle. It is a negatively charged particle. It's basically an electron getting shot out of a atom that's undergoing decay, and it is a little bit more penetrative than alpha particles. An electron is a subatomic particle. It's pretty small. It's negatively charged, and it is not in the nucleus of the atom. It is found orbiting around the nucleus of the atom in what we call the electron cloud. So just a big space where electrons fly around. And that's what the electron cloud is. Gamma ray is the third type of nuclear radiation that we are covering. And these are actually just energy rays that occur when there's some rearrangement of particles in the nucleus. So there's no actual particle that actually shoots out of the radioactive atom. It's just energy rays. And so gamma is very penetrative because there's no actual particle that can be stopped. It can penetrate through your entire body. You have to use like thick lead shields to protect people from gamma radiation. Half-life is defined as the amount of time it takes for half of a radioactive substance to decay. So if you have some radioactive material like some uranium, you have 5 grams of uranium, it decays at a constant rate, and the number of minutes or days that it takes for half of that 5 grams to undergo decay is the half-life. Ionizing radiation, so alpha, beta, and gamma are all forms of ionizing radiation. It basically means they can cause damage to cells. They hit things and cause them to become ionized, and that's very damaging. An isotope is, so for let's say carbon is the classic example. All carbon atoms have 6 protons, because there's a 6 above the C on the periodic table, but they may have different numbers of neutrons. So all atoms that have 6 protons are carbons, but not all atoms that have 6 protons have the same number of neutrons. So there are different isotopes of carbon, and because they have different numbers of neutrons, they also have different masses. So different isotopes have different mass numbers, which brings us to mass number, which is just the sum of the protons and the neutrons. So it's a whole number. A mass number is going to be an integer, like 12, 13, 14, versus atomic mass, the number on the periodic table, which usually has, several numbers after the decimal point, because it's an average. A nuclear decay equation is sort of the chemical equation that we can write to show how an isotope goes through decay and loses one of these radioactive particles. So it's similar to a chemical equation. It's a type of chemical equation. Nuclear radiation is the type of radiation we discuss in this chapter. There are other forms of radiation, like the sun, electromagnetic radiation, for example, light, sound waves. So alpha, beta, and gamma radiation, however, happen to be forms of nuclear radiation, types of radioactivity that are given off by the nucleus of atoms. A neutron is another subatomic particle. It is neutral, it does not have a charge, and it is found in the nucleus of the atom. The nucleus of the atom, or the nucleus really of anything, is the center of it. A proton is the third type of subatomic particle, and it has a positive charge and is found along with the neutron in the nucleus. Radioactive basically means that, like if an atom or an isotope is radioactive, it means it undergoes radioactive decay and it can produce one of these types of ionizing radiation, alpha, beta, gamma. A radioisotope is an isotope that is radioactive, that undergoes decay. Not all atoms do this, and in some types of elements that are very large, all of the isotopes, so like all of the isotopes of uranium, are radioactive. But there are only some radioactive isotopes that are in the smaller ranges, like phosphorus. There are some radioactive forms of phosphorus and some non-radioactive forms of phosphorus. So we identify radioactive isotopes as radioisotopes. Subatomic particles literally means the particles that are found within an atom, or they're sort of smaller than the atom. And those the three main subatomic particles are protons, neutrons, and electrons, which we've already described. There are others, but those are sort of higher level physics that you get into that. And then lastly, a tracer. One of the medical uses of radioisotopes is to use them as a tracer, a medical tracer, so you inject them or ingest them, and they leave a trail through the body. Basically, they emit radioactivity that can be read by a film or by a machine, and then you can see where it goes, where it travels, and it can highlight, if it localizes to certain organs or cells, it'll highlight those in a way that you can't see without using it. So it's almost like a radioactive dye that can be used in medicine to look at different organs, to image them, or to see if they're functioning properly.